Hello, everyone. Thank you for joining us in one of the, preferring this talk over the three competing talks going on right now. Yeah, so this is one of the really hot topic in this particular conference because you would have seen other talks. Maybe, Peng is here. I was just talking to him about the PPL observability stack. There was another talk from the Uber folks on gRPC stuff. There was a talk yesterday on more on the DataFusion side of things where they're trying to connect the dots between accelerating query engine using DataFusion or less technology. So this talk is kind of trying to address the foundation of what all of these would need, because what we are trying to target here is how do you evolve the OpenSearch communication framework to a streaming which is more standardized, and then use Apache Arrow flight, which we'll talk more in detail, to kind of make sure that we up-level the platform and make it ready for those kind of use cases. So my name is Saurabh. I'm part of the OpenSearch team at AWS. I lead the search and infrastructure group. I have Vamsi with me. He'll kind of dive into some of the technical aspects of the implementation, what we have done so far. He's an engineer on the search side. So let's get started. This is pretty much our roadmap for the session. We'll start with some of the details on how OpenSearch query engine has been evolving from the traditional style to the new streaming world. We'll talk about some of the real-world use cases just to map it better, like for your better memory mapping, saying that how the general searches work today, and maybe with the streaming, how they would maybe outperform the current scenarios. We'll do a little bit of tech dive into the Apache Arrow and Flight, which are the core of this whole work that is happening on the streaming side. On the aggregation framework, we'll delve a little more, because that's the key of this implementation that is already out in 3.2. We'll talk about term aggregations, how it is getting accelerated. Then we'll get into the performance wins in terms of some of the popular benchmarks that we have, like ClickBench, and see how OpenSearch is doing with this new change. Setting the stage for the multi-engine, multi-format, which is my favorite topic. We'll try to spend some time there towards the end to make sure that we have a little bit of coverage and connection with the other talks that we have had. Please hold on to your questions for Q&A at the end, and then we'll try to address them based on the time we have. So OpenSearch as an engine, I think, doesn't need any introduction. Like, we all have been here in these conferences. We have been hearing about great work that OpenSearch has been helping with, like search, log analytics, observability, security, vector, ML, and AI. So this, I think, we can fast forward. But what is important is how the OpenSearch engine is evolving. So OpenSearch was kind of built in a very traditional way of a traditional search query engine where the request lands onto a coordinator node. It is fanned out to data nodes for individual execution of data that is sitting on those data nodes. These data nodes have usually the shard information. So these shard results are executed on the data node, which is nothing but probably a hit or also maybe an aggregation bucket. Now, once all of this is compiled, it is sent back to the coordinator, and then coordinator does the heavy lifting of merging this result, doing any reduce operation, and sending the response back to the client. So that's a very typical way of how traditional query engine worked. So this has worked pretty well for a very long time. It's working right now. The only challenge which comes with this style of scatter-gather model is, or I would say more like a batch and then gather model is, when the data grows in your analytics system, your system starts to show issues with respect to memory, and also can lead to some of the computation issues at the end of the coordinator when it kind of does the merges. So in response to all of that, the streaming paradigm is a shift which kind of changes this model from batch then merge later to kind of continuous merging that happens on the coordinator node. So data nodes, as they are kind of gathering or collecting this information, or even fetching this information, they can keep sending it to the coordinator without having to wait for the entirety of the time. Now, what are the driving forces for this? So driving forces is, of course, one, as I talked about, how aggregation framework is going to use it. We'll dwell a little more into that, getting into the specifics of how it is kind of helping there. But I think the other ground where it is also helping is setting the ground for the other use cases like joins. Just a recap on 3.2, where we kind of launched this in form of a streaming aggregation framework, which was used by term aggregation, and which for the numbers we'll talk about a little later. So now, the obvious question is, like, yes, there was a traditional style of doing this query execution, and now with the streaming, why are we picking this as a new approach? Could there be something else? So let's break this down in terms of the relief that streaming brings into. Typically, when we think about a term aggregation with a very high cardinality field, there will be a huge map of memory buckets that created on each data node while kind of executing this. And then, of course, there would be other structures like priority queue and stuff like that. However, with streaming, you get the ability of not holding onto this memory for a very long time, but rather sending the batches in a smaller chunks of data back to the coordinator node. Now, because you have less data sitting on the coordinator node, your garbage collection gets eased because you don't need to kind of collect as many objects by the JVM collector, and then you have fewer GC pauses, and of course you have more stable tail latencies. The other thing what it also helps is isolating your workload and scaling better, because now your data nodes can be much leaner versus your coordinator can be beefier, which could be about, let's say, 10% of your entire fleet, and that way you can let data node do only the retrieval job versus coordinator can be more specialized and scaled for doing the merges and some of the high memory intensive and CPU operations. So the earlier results what we were talking about in 3.2, we have seen like about 30 to 50% reduced latency and also about 2x higher throughput. We'll go into those metrics and also talk about some of the popular benchmarks like ClickBench to kind of show how we are kind of helping with those. And the way we kind of touched upon this is basically how this all plug and play together so that we can do better cross indices joins. So let's take that example here. Like for example, if we were to kind of think about a retail website which is doing a Black Friday sale and people are kind of searching maybe a wireless headphone, there are like two requirements to this particular use case for a query to execute efficiently. One is you need to kind of get a type ahead suggestions based on the catalog index that we have, and then you'll have to map it with the profile behavior of a user because they would be located in a certain geography, they might be having certain preferences. Today, doing this in OpenSearch would be a challenge because one, you can't do cross-index joins if your catalog and user behavior are like two different indices. You might be able to do something with maybe at SQL level, but what it means is that you are gonna pre-compute a lot of result at the coordinator node, then you try to merge them and then try to kind of cut it down, which is kind of inefficient and slow. The challenge is also around the concurrency that you can reach and amount of the memory that you would need if, let's say, you also want to maintain facet counts and things like that. With streaming, some of these can be done in a more efficient manner because now your fast autocomplete results, which are streamed back from the data nodes, can be streamed together with the responses coming from the other index, which is user behavior, on the coordinator node. And one of the clear aspects of this is what I think Fro and Mark talked about in yesterday's talk, is that you can always fan out the work that is happening on the coordinator into dedicated workers. So that way, your joins could be efficiently scaled out without needing to scale your data nodes per se. So at the end of the day, you get better efficiency and your outcomes for the search query latencies are pretty pretty good because you don't kind of burn your cluster while trying to handle this kind of load. Similarly, if we kind of talk about a use case on the analytics side, if we take that same example and let's say you were trying to do an analysis on your unique IPs across different geography that you have and try to kind of get a visualization dashboard on a per minute basis for a 24-hour window. So if you had to do that, imagine if you have like 10K IPs in US East 1 and you have 10K IPs in US West 2. In that case, you would need to kind of create all of these memory maps on the data nodes and then send all the results all together back to the coordinator, which means you create big arrays on the data node and also on the coordinator when you merge them. Versus in streaming, you don't need to kind of hold these objects into memory, but you can send them as and when ready while your coordinator can merge on the fly. The important aspect also comes with your experience of real-time dashboarding, because now your dashboard doesn't need to wait for this query to entirely complete, but rather it can start loading the objects as and when these merge results are coming. And it's better experience than nothing, and everything versus you kind of start filling up early as soon as your data is available. The other important aspect is sometimes in a very distributed manner, your data nodes could be loaded differently. So if, let's say, one data node is running slow, it would still be able to kind of send back the results at a later point in time versus your dashboard can start still populating the results while the last pieces kind of come in at a later place. Now, going back to our examples for joins, this would help with some of the use cases for trace analytics, like if you want to kind of do joins between logs and traces, or if you were to do joins between your metadata and probably anything that has to do with the metrics. So all of these use cases can potentially be solved if we were able to support these joins happening with the streaming data that's kind of coming in. So the bottom line, what we're trying to say is that overall with this Arrow approach of streaming, it kind of opens the gate for observability workload to be more powerful and be executed under a single pane window within OpenSearch. Now, how is this all happening? So one of the very key aspects of this is Apache Arrow, which is kind of a backbone to all of this. So if you have to take an analogy, think of it like it's kind of, if data is like a music, then Arrow is kind of a sheet music which every musician or every instrument can understand without having a dedicated notation for each. So the important aspect of Arrow also is not just the interoperability, but also that fact that the data is in columnar or in-memory format. So if you had, let's say, 1 million log entries, and then you have, let's say, a status code as a field, all of these million status code would be stored in the contiguous memory locations so that they can be accessed much more frequently. And similarly for other fields, let's say if you have timestamp, messages, etc. Now, why do we care about this? Like, how does it really help? So if you were kind of storing these data sequentially, it can be like the retrieval of this data can be magnitude faster than chasing pointers, which would typically happen in a row-based store. Also, modern CPUs, they love these sequential data because then it helps them with their cache prefetch operations, which is very efficient. Also, with the bonus, what we get is like SIMD instructions because let's say if you were to kind of line up this data, you can actually operate on a value of, let's say, 8 values together or 16 values together instead of one value at a time. So it's kind of like reading sentences instead of just reading one word at a time. The fact that Arrow also kind of gives you the zero copy and interoperability, some of the things which we also had covered in the previous talk, was kind of empowers you with the fact that you can, OpenSearch can compute all of these results, let's say, which is in a Java format, and it can be consumed by a Python client. It can be transferred to a Rust library, which could be, like a DataFusion, or it could be, used by any other, tools like Jupyter or something. So essentially, what we are trying to say is that it kind of eliminates the need to serialize and deserialize data, just because it's a universal language agnostic format. Yeah, so I think the essential things what we are talking about is this is not the new concept that we are trying to bring in. It has been a known and proven concept that other databases have also kind of gone into, and they have built big out of it. Like for example, Spark, Pandas, Snowflake, there have been some examples which have been using it pretty much efficiently. So kind of opens the door for OpenSearch to kind of be into the same zone of interoperability and also move towards the extended usage of external engines. So let's look at the other aspect of things. So while we talked about Arrow, which is the in-memory representation, the aspect of transferring this in-memory objects and then be able to send across the wire is also super important, and that's where the flight comes in, which is the network side of the Arrow. So think of it like, as the name goes by, if Arrow is the data, flight is like the highway or the skyway to kind of just send it efficiently. It is built on the gRPC and is optimized for sending Arrow batches. The important aspect is like bi-directional, and it can help with parallel streams. So going back to the join use cases, what we are talking about. So if you had like 10 shards for your catalog index, if you have 10 other shards for basically your user behavior index, then you can actually stream all of them in parallel. And the bi-directional nature of it kind of helps maintain the momentum at which coordinator is fetching this data so that you are not loading your data nodes to an extent which they are not capable of. Also, if you look at some of the ways of how it has evolved so far, there are enough papers out there which kind of talks about how it has outran the traditional JDBC or ODBC for database retrieval operations up to like 10 times. So we are talking about of a magnitude saying that from 100 MB per second scale on JSON, you can actually move like a 1 GB scale on byte format if you're just moving to the flight. In OpenSearch, I think exposing these flight endpoints could be another step, which is not yet available, of course, because we are still using it for node communication. But the moment if we kind of want to stream the search results back to the client, and imagine if you have like a an endpoint which is like _flight, then your clients could actually collect this information or collect this arrow data directly, and then client can help send this back to the clients without having to use any deserialization or serialization of JSON format. And also, it kind of helps with the horizontal scaling. Again, taking the same example, because big aggregations can now be served across by delegating the responsibility to users, because each of these nodes can do their own merges and use the flight streams to kind of send it back to the single coordinator or directly to the client. So now that we have understood the basis of like how OpenSearch is using the streaming format, and then also probably using flight and arrow, let's dig more into like the specific use case of types of aggregation, and probably the term aggregation, where we have kind of launched this in 3.2. And I'll let Vamsi to conclude.
Yeah. So Saurabh set the stage for what OpenSearch does today, and also why we need to look at aggregations as our big log analytics use case. So I want to briefly talk about, and also I think he set the stage for the technologies that we're trying to use here. So I want to set the stage for what aggregations are and what are the types of aggregations that we are targeting for this use case. So broadly, OpenSearch has 3 main aggregation types. The first one is the bucket aggregations. So bucket aggregations comprise things like the terms aggregation, the range aggregation, the histogram, the data histogram, and so on. So you can think of bucket aggregations are like trying to group things into individual buckets based on their keys. So for example, a car dealership might say, okay, give me all the counts of my different car models. So it'll say like, oh, I have like X number of Elantras, X number of Sonatas, and so on. So bucket aggregations are really powerful because you can nest bucket aggregations with other bucket aggregations, so it becomes like a multi-level bucket aggregation. The second type of aggregation that we have in OpenSearch today broadly are the metric aggregations. So for example, in the SQL world, you could say something like, give me the values of this query, but also give me the counts or something, or give me the min and the max of this field. So metric aggregations are really powerful that way. You can obviously configure a bucket aggregation to also have a metric aggregation within it. So you can say, okay, for this bucket, what are my metrics? What's my min and max value for this key? The third type of aggregations that we support, although they're not in the same class as the other two, are the pipeline aggregations, where we can compute the aggregations. So as the name suggests, right, you could have multiple pipelines of aggregators where the output of one aggregator flows as the input of the next. So you can compute these moving averages and moving derivatives and so on. So now that we have an understanding of the different types of aggregations that OpenSearch supports, I want to just stick to terms aggregation. Now, the terms aggregation is by far the most popular aggregation type that most users run, right? Probably something like 80% of users run terms aggregations. So this is what a simple terms aggregation looks like. At the top, you have the size attribute at the outside. So that tells you that, okay, we're running this query. There's no hits I want. I just want to get the aggregations for this query. And here we're aggregating on the field, which is the response.keyword field. And we're saying, OK, give me 10 buckets, the top 10 buckets for this field. And I want them in descending order of their bucket count values, right? So before we talk about how this term aggregation works in OpenSearch, or why we're doing what we're trying to do, I quickly want to show you the results that we've achieved. So on the left, you can see the CPU utilization for the traditional aggregations framework that we have today. As you can see, we have 2 data nodes, and we have a coordinator node. And as the aggregations are running, you can see that the data nodes start to spike up in CPU, because aggregations are very CPU intensive. And so they're starting to go up, and then eventually, once the query workload is done, they sort of come back down. On the right, you can see with streaming aggregations, we're seeing 50% lesser CPU on the data nodes, right? Pretty impressive. Now, CPU is not the only thing that we're able to improve, right? If you look at the JVM metric, this is a very popular metric that a lot of users care about. You can see in our traditional aggregations, the JVM is pretty spiky. It's averaging about 75-ish% of JVM usage, whereas in streaming, the JVM is not spiky anymore. It's sort of more uniform, what you'd expect. And then we're also seeing about a 30% lesser heap utilization. Also impressive. But really impressive is this, right? So this is the latency metric, the response time for this query. On the left, you can see that in our traditional aggregations framework, you'll see this big, long spike, which I'll explain briefly why we're seeing such a huge spike in the latency initially. And then over time, it sort of comes down and then averages out to about 2.5 seconds for this query. In streaming, we're seeing the average latency for this query at about 230 milliseconds. So that's a whopping 8x improvement in latency. Right? So to understand how we achieve these results, we need to understand first how do aggregations work today, or specifically how does a term aggregation works today, and where the bottlenecks are. Right? So coming back to the same terms aggregation query that we have, you'll see that when the query hits the coordinator node, it gets fanned out to all the shards, and each shard processes that aggregation on the data that's available to it on that node. So depending on the type of aggregator that you have, you'll decide what aggregation, or depending on the type of aggregation you will have, you'll decide what type of aggregator to use. So each shard runs the aggregation on its local data. So a shard some shards might have more data, some shards might have lesser data, so depending on that, you might see different latencies. An aggregator on each shard is responsible for executing the aggregation, like we discussed. And once the shards process the data on their nodes, they return the results back to the coordinator node, where it merges the results that it's getting. It's doing a bunch of reducing operations, and so on. We'll talk about this in a little bit. The next thing I want to talk about is something called the ordinals. If you attended Froze and Mark's talk yesterday, you'll already see where I'm going. So ordinals are these memory-intensive objects that OpenSearch has. So ordinals are very simple. They map values of that field to numeric data. Why do we need to do this, right? So before I talk about ordinals, there's two types of ordinals. We have segment ordinals that work at the Lucene segment level, and we have global ordinals that work at the OpenSearch shard level, right? And the reason that we do this is because each segment will have its own set of values. A shard will obviously have a bigger set of values for all of that segments in that shard. So we want to have a global mapping of all that ordinals. So in this example, a status code of 200 or a status code of 404 will be mapped to ordinal 1, ordinal 2, and ordinal 3, and so on. So why do we do this mapping, really? Because aggregating on these numeric ordinals is significantly faster than aggregating on the values themselves. In this case, the values happen to be just like 3-digit status codes. But let's say you have a keyword field, and your keyword is like 30 characters long, right? You don't want to keep aggregating on that data. You want to reduce that down to just a single digit, like this, right? By default, global ordinals, which are obviously different from segment ordinals, are built lazily on the first aggregation result. Now, if you remember that chart where the latency sort of spiked up initially, that's because that request had no global ordinals built. So the first time that request lands on that node, it needs to go and build that global ordinals map, which is seemingly a very time-taking process. It then stores that values in the field data cache, and then for subsequent requests, it's able to use them. So that's why the latency drops back down to about 2.5 seconds. Still pretty bad, but much better than that 10-second initial latency. Another object that aggregations use are the big arrays. So if you've ever worked with the OpenSearch code base, you'll see that it's littered with these big arrays. Now, big arrays are essentially the data stores for the aggregation itself. So they're very memory intensive, and I'll explain why. So they're the core data structures that aggregate data. So a big array is essentially just an array, but it's an OpenSearch's take on what an array is. The reason that it's different from regular array is because it's able to dynamically and efficiently grow and resize. So a big array might be initialized to a certain size, and then depending on how much more data it needs to see, it will dynamically grow on the fly. It's also designed to be heap conscious, so it's able to essentially manage memory better than what a regular array can do. You can hold strong references, weak references, and then the garbage collection will sort of take place when necessary. Now, big arrays are essentially the core data structures that at least the term aggregation predominantly works on. Another piece of the aggregation framework is the shard level reduce. So if you remember, I said that the aggregation happens at the shard level, and once the shard computes its data, it then returns all of that results back to the coordinator. So before it's able to return those results, it does a reduce on the shard. This is also a CPU-intensive operation because it holds a priority queue, right? It holds a priority queue of some values. So let's say I'm requesting 10 results. Each shard will have, the formula that we use today is times 1.5. So if I'm requesting 10 values, it will go and compute 15. So it'll multiply that by 1.5, and then each shard will then return 15 results back to the coordinator. Obviously, there's more than 15 results in that shard, right? The shard is going to have a lot of data. The aggregation is going to run a lot. So all of those results get stored in a priority queue. And new incoming results are vetted against that priority queue. And if a new result is deemed to be suited in that priority queue, it then just gets inserted or gets updated in that priority queue as necessary. So this essentially helps us eliminate a lot of the aggregation data space. So let's say on that data node, there's like thousands and thousands of aggregation buckets that we're creating. We just need to know the top size times 1.5 buckets. So that helps us reduce the amount of data that we're sending to the coordinator node. Now that's always not a great idea because you can lose out on some accuracy because you're not sending all the results back to the coordinator, you're only sending a small portion of that results. And the last step in the aggregation framework is the coordinator reduce itself. So once all the shards return all the results back to the coordinator now gets, well, we only requested 10 results, but the coordinator is now seeing 15 results from each shard. So it needs to take all of these 15 results and then combine them back down to just 10 results. So it does a coordinator level reduce. Once we do that reduce, we essentially return back a bunch of buckets. Each bucket has a key, which is the term that we want, and then the doc count for the numbers that we're seeing itself. By default, we just return 10 results in the aggregation framework regardless. So if you mention a size of 500, then we'll return you 500 results. Okay, so now we've sort of set the stage for all the pieces that happen in the aggregation flow. And now we're already seeing things that can be better, or at least we're seeing where the bottlenecks are, right? So what are some of the constraints with aggregations, right? So obviously, the more the document space, the more compute and more latency, right? So let's say if I have a query filter that's filtering on a large set of data, and then if I have an aggregation query that's running on a field that has a very high cardinality, we're bound to see a lot of compute and latency happening. Now, the example that I showed is just a simple top-level terms aggregation. Most users in practice don't run just a simple top-level aggregation. They'll run multiple aggregations, multi-level aggregations, sub-aggregations, nested aggregations, and so on. So really to understand the complexity of the CPU space, you have to multiply the cardinalities, multiply the spaces of all of these together. So if you have A, B, and C, you have to multiply them all together, and it becomes a very large aggregation space. Now, obviously, when the request lands onto the coordinator, it then sends that down to the shards. The shards compute the values. And then while the shards are doing their work, the coordinator node is really not doing anything. It's just like sitting there waiting for the shards to return their results. And the shards can take seconds in some cases, maybe even tens of seconds in some cases to return the results. So the coordinator node is really not doing much work. Now, what does this look like in practice, right? So these are some things that you might see in practice, right? You might see like your CPUs spiking 200%. A lot of times it's because these expensive aggregation queries are running. You'll also see the heap utilization. Now, like I said, we have these ordinals, you'll have these big arrays. They're all sitting in memory, sitting in the heap memory, and they're sort of consuming the heap. So the more the document space, the more complex the aggregation, the more the size of the big array, the more the size of the heap used. And then this is obviously latency. You'll also see like a lot of regular search queries taking milliseconds, tens of milliseconds, hundreds of milliseconds, but then suddenly aggregation queries are taking seconds, maybe even tens of seconds. I've seen queries even taking minutes, right? So these are some of the hard constraints that you'll see on your cluster. But you also have some soft constraints, right? So a lot of times you'll have these errors show up in your logs where you'll have like, oh, I have too many buckets exception because you're trying to have these multiple nested aggregations. Or you might see these circuit breaking exceptions where you're saying, okay, I have my heap size is X, and I've configured it to be X. I have a threshold of like maybe 75% or 80% or 90%, and then these big arrays are really growing in memory, are growing in size, and then they're consuming too much memory. And now I don't have enough memory for everything else. So now you have this aggressive garbage collection that's happening. So what are we doing about this, right? So now we've introduced streaming aggregations. Streaming aggregations have two parts to them. One, we have a custom streaming transport, and we have a custom streaming aggregator. Why do we need a streaming transport, right? So the current transport works on a default netty protocol. The new transport, which uses flight, which Saurabh talked about, runs on gRPC. So you now need to have a new drop-in transport that's able to send and transport arrow-based messages across the wire. And all of the serialization and deserialization logic is now handled by Arrow. Now, the transport itself is not enough, right? We have to make changes to the framework also. So that's why we have a new custom streaming aggregator. We call it the stream string terms aggregator. Previously, it was the global ordinals string term aggregator. And I'll talk a little bit more about this. And we also have some new algorithmic changes that we've been able to incorporate for us to save some memory and improve latency. So the streaming transport itself, it's a new flight, Arrow flight server. So there's OpenSearch obviously has a REST server running on port 9200. It has a transport server running on port 9300. And now we have the Arrow flight server running on port 9400. There's also a new Arrow flight client, because when you have a server, you obviously need to have a client. So server sending Arrow messages to the client, and the client's able to read those messages and decode those messages. The one cool thing about Flight is that it has a bi-directional stream, which is a little bit different from how Netty works, right? So Netty, you send a request, and then you're like waiting for that response, and you get a response, and you close that connection. Here, you start a stream. The stream is opened between a node and another node, and then you're saying, OK, give me my next batch of data, give me my next batch of data, and you keep requesting new batches of data until the stream is completely exhausted. So this helps with like stream back pressure. So if you have too many batches that are being processed by one node, you can say, OK, hold on. I don't want to request a new batch until I need to. And now we've designed this new transport to be like a drop-in replacement in the future. In the future, if you want to get rid of the default transport and make Arrow Flight the only transport, we're able to do that. We also have the streaming aggregator, which is where a lot of the magic actually happens. What did we do? We replaced the global ordinals. So we now no longer we now no longer compute global ordinals. We don't need global ordinals anymore. We just stick to segment level ordinals. So we don't need to do that expensive operation of building global ordinals. We don't need to do that expensive operation of computing the segment ordinals and mapping them to the global ordinals. We got rid of that, right? We're also flushing per segment instead of shard. So this is very important, right? Like I said, an OpenSearch shard is built out of multiple segments. So when the aggregation query runs on that shard, it runs on each segment, and then it waits for all the segments to finish, and then it does the shard level reduce, and then the coordinator can do something about it. What we're doing now is, once a segment finishes its computation, it returns that data back to the coordinator immediately. We no longer use the priority queue. We got rid of the priority queue. We got rid of a bunch of things there. So yes, we no longer have the priority queue, so we skip the shard level reduce. We're sending all the results back to the coordinator. This is great for two reasons. One, no priority queue, less computation. We don't have to wait for the shard to finish its operation. The second thing is, previously we would only send size times 1.5. So we're missing a little bit of that accuracy. Here, we're sending all the results back to the coordinator. So you're guaranteed to have 100% accurate results. Another very crucial, important thing that we're doing is we now no longer grow that big array. That big array that was just growing monstrously in memory, we now no longer grow it. Once it grows to a certain size, we use it, and then we just kill it. We reset it. And this is very clearly seen in the metric here. As you can see on the left, in the traditional aggregation framework, the big array's memory was going up to like 4 gigabytes of heap memory for just one query, whereas in the new streaming aggregation approach, it's like 200 MBs, right? So it's almost 20x better in terms of the heap utilization. This is just running a single query on a single term aggregation. It's going to get much better in the future. Yeah, so Saurabh is going to continue talking about why columnar formats matter. So.
Yeah, thanks, Vamsi. Now that we have understood the term aggregation, we have looked into the possibilities what happens like again. We just want to kind of look into where this whole work effort is headed. So Apache Parquet is like a, it's kind of a little bit of a bigger picture. So it has been the de facto columnar store for a very long time. So if you have data, data lake probably is already using it. However, and also Parquet is kind of pretty much optimized just because it's using columnar format again, it's storing similar data together, so it's great at compression. It also has some metadata which can help you skip the chunk and go to the point where you have the data that matches the query. But if you look at historically, if you had to kind of ingest the Parquet data, you would need to kind of translate it to JSON or use a bulk API and then ingest it into OpenSearch in a traditional way. But just because Arrow is nothing but Parquet memory or Parquet is nothing but Arrow on disk, the interoperability, if OpenSearch starts supporting Arrow, would be very much achievable by just reading the Parquet data directly from the disk. So where Parquet data can be an extension like another segment or maybe even a qualitative set for OpenSearch. We also wanted to touch upon the vortex because it has been an exciting development. It kind of think of it like it's an experimental leading edge columnar format, and then of course the people behind it kind of think that it's better at compression and vectorized reading algorithms. The reason why we are mentioning is this because OpenSearch is evolving into an ecosystem with this integration, and tomorrow if vortex gains more popularity, because it's already kind of on this foundation, it will be very easy for us to accelerate and get integrated within the OpenSearch ecosystem, and probably we can think about how it can be an extension as another story. Yeah, I think in terms of the alignment, this is not just happening in isolation. It's kind of where the data world is headed, and that's where OpenSearch typically has been using the same stock format. Anyways, like all the doc values that we have has been columnar historically, but Arrow and Vortex kind of is taking it to the next level for better standardization and performance and also interoperability. Yeah, so I think the benefit recap is pretty much the same. A lot of things that all you are getting in terms of the columnar and being able to do simply. We can be a little bit more about simply. I can just quickly run through it in terms of the key here is being able to kind of achieve vectorized distribution. So let's say in a traditional query format, you see is kind of trying to match doc IDs that we put one by one, and trying to find out how many doc ID matches the query. Versus if you had, let's say, a certain condition of 1,000 and 1,000 docs, and then if you are matching certain value greater than 100 or something like that, if you were to load all of this value into, let's say, a 256 bits of data set, maybe you're operating like 8 or 32 bits value each at a time. So you could just kind of take 16 values and execute it like one instruction. And that's typically how the secret is to prove them and give you the flexibility of being able to kind of accelerate these execution. Again, one of the other things what it also gives you is being able to be more like branching, because I think Apache Arrow was optimized for that. We have seen some of the real-world examples like WPP point, like certain way customer revenues and rate speed already establishing a complex execution. Now, just being the foundation for the future, we just want to kind of close out by talking about how streaming is one thing that we have already started integrating on server side, but that's not the end of it. Of course, we are thinking about how streaming can be extended into maybe next pipelines, how we can open the possibilities of having a live query update, where you can have like dashboards which can keep on streaming data as and when it's coming. So there's a lot of future extension work that we go with. Of course, SIMD is, we talked about, but there has been some work that is done already, like in terms of logic computation using NVIDIA bits and all. But with the possibility, we want to kind of move towards a more hardware accelerated execution, which is totally a new possibility which opens up with this kind of interfacing, and then with material format indices, which is kind of the personal favorite idea that I'm kind of covering here. Is because the moment we kind of get this multiple indices supported, we can move to the direction of already either the more better tiering, where you can move the data into Parquet and have the raw data in the scene, or you can have more use case-based isolation, saying that your searches put down on the zero analytics can move to a different format altogether. Ecosystem integration is also kind of important because I kind of touched upon it in the beginning. Typically, the moment we kind of give an endpoint, let's say Jupyter or any other notebook can directly kind of go ahead and integrate with the data frame results that's coming from the OpenSearch directly without having to do any serialization. We have already started seeing one integration happening in our ML pipelines because it's kind of a plugin that is used by OpenSearch, but all of its interaction with external engine or basically ML engines, it's kind of starting to use this streaming as a platform. And of course, the community contribution is also kind of super important. We have already seen great work happening between AWS, Uber, and other folks. There has been a lot of traction on it, so we would kind of look forward to seeing this cross-coordination happening and more this coming out this year. This is just to mention one of the talk, which kind of covered some of the integration with DataFusion yesterday. So this is the high-level diagram where we were thinking about how multi-region format could kind of be a future for research with all of this foundation of already being done. And if you haven't seen this talk, I think probably post on YouTube by a couple of folks on our camp. Yeah, right at the end, I think we just want to close out on saying that if you haven't tried this feature, it's available. If you got to try it, it's very easy. You have to just enable a certain kind of labels, streaming format communication. It's kind of available in as a drop-in plugin, which you can install by default. You just need to kind of add this particular flag into your request, and you can start using this particular flow, and then what you get is better. All right, yeah, I think that's pretty much about it. Any questions?
Do you have performance numbers on between streaming aggregation and the bucket aggregation methodologies?
Yeah, I think that's the number what Vamsi covered pretty much there. And then there are like different dimensions of these numbers around CPU, memory, and also latency, I would say. So this one is particularly around the CPU utilization that you see. The left is the traditional stack versus right is the new streaming aggregation that we have. Similarly, this is the heat memory utilization, which is kind of pretty much more stable than 12 to 50%. And this is latency. So like from 2.5 second, it dropped down to like 1.2 second.
Yeah, I think in 3.2 we only support the we support terms aggregation or top-level terms aggregation with metric aggregations and so on. We don't support sub-aggregations or multiple bucket aggregations yet because there's some nuances to making that work. But in terms of the numbers itself, right, the latencies are like, on average, we're seeing about 8x better latencies. And every other metric that we're seeing, whether it's CPU utilization or whether it's garbage collection or whether it's JVM memory, is way better across the board.
So, sorry. So you said you don't support bucket aggregation just yet. Is that something on the roadmap? Or
yeah, that's fine. So with 3.2, we started with some of the work that has been done because I think it kind of takes to redo your aggregation framework, what we talked about, like streaming aggregation or something we use. And now other aggregations are going to onboard it and then
so to be clear, like terms aggregation is a bucket aggregation, just that we don't support the other types of bucket aggregations. We don't support multiple bucket aggregations, one nested below each other. But that's on the roadmap. I think in 3.3 and 3.4, we're going to expand this to most aggregation types. And we do have a plan to enable this by default. So you don't have to change your query parameters. You don't have to enable any flag. It'll become the default experience out of the box in the next few releases. Yeah, maybe I can talk about the cons. So obviously, what happens traditionally is that you would have all of these segments computing their data locally, and then the shard would just return all the results back to the coordinator in one single hop. Right? Now we're seeing a lot of data being returned from each segment. So you could have 30 segments in that shard or 40 segments in that shard. So you're seeing more network bandwidth usage. So that's one of, I wouldn't say it's a con. I would just say that that's something that will go up as such. Now, that being said, streaming might not be useful in all cases, right? If you really have like a very, very low cardinality field, maybe streaming is not the right one for you. Or depending on the type of aggregation that we're running, it might not be right. For example, maybe you have multiple buckets of aggregations and you want to return. Previously, we would just return like, okay, for this shard, I'll just return 15 results. Now I'm saying, okay, I will return every single thing back to the coordinator. So you do risk blowing up that coordinator. So we're trying to prevent that by adding guardrails where possible. So that's why we're taking this in an incremental approach where eventually we just want to start with the top level and then eventually we'll expand this as we go.
Right, I think we're running out of time, but if you have any more questions, we'll be around in this conference. We can catch up offline, and of course there are GitHub issues and PRs around it. So if you want to learn more, just feel free to comment and reach out there. Thank you, everyone.